Welcome, my name is, again, James Rennie, and to jump right into things, the title of my model is What is the Impact of an Invasive Species on an Ecosystem? Now, in this model, we'll be studying three primary or indigenous species. Now, I don't know how many of you are familiar with the Pacific Northwest's indigenous species, but the three that we'll be looking at are the great blue heron, which will be at the top of our food chain, the trout, pretty much any breed of fish that exists in the Pacific Northwest, and then the newt, which is going to be at the bottom of our food chain. And then we're going to be introducing the bullfrog. Now, the bullfrog was brought over in the 1800s with a lot of the migration that happened west. It was brought over by a lot of French people of French origin because they needed a food supplement and they were used to frog legs, and bullfrogs can grow really big. The problem is that they come from the south where they have a lot of really big predators like alligators and anacondas and stuff like that. They came to the Pacific Northwest where we don't have as big reptiles and as big of predators, and they just grew wild. A mature bullfrog, there's pretty much no predator that can eat that. So the only place we see them actually being killed is in the tadpole and the egg and the adolescent species. So to jump right into things, I started building my model, and I started really simple with a two-step aging chain for the herons. We have the adolescent herons and we have the mature herons. The distinction being that the mature herons are going to be reproducing, they're going to be affecting this heron births. The adolescent herons will simply be growing into mature herons, and then we'll also have the heron death rate, which is will be dependent later on food, as you'll see. Also, the same exact thing for the newt and trout models. We're going to skip bullfrogs for the time being because first we need to establish a stable ecosystem before we can destroy it. Then I added in some death rates for the adolescent herons because, as you may have noticed before, the younger breed of herons were not dying. And then the same exact thing for the trout eggs and the adolescent trout, as well as the newt eggs and the adolescent newts. So that's just death rates there. And again, those will be dependent on food. So now, up until this point, all of these models were completely independent. They didn't even need to be on the same platform because they were just generic growth of one species. So in order to get a good relationship, a food chain, and one model that was working together, I had to put it all together. And the way that I did that was through the addition of a predator-prey dynamic. So here we have the basic trout model up there, and what I added to start getting some interactions and some greater feedback loops in here were herons, specifically in this case the adolescent herons eating the adolescent trout. So the younger herons, as they're growing, are going to be fishing, and they're going to fish for the smaller fish, which is the adolescent trout. So now we have some interaction going on. I also added pretty much the exact same thing, and sorry that's a little bit hard to see, but we have the mature herons eating both the mature trout and the adolescent trout, and that the amount that they eat is actually proportional to, or is a percentage of the population. So if trout are very prolific in a certain year, they're going to eat a lot more because there's going to be much more abundant food source. If they're much lower, they're not going to be able to fish as much and will eat much less that year. So next, what I did was I added a relationship between the amount of available food and the birth and death rate. So in years when, say for the herons, if there are a lot of trout, they're going to be able to eat a lot, and their lifespan is going to end up being their sort of normal lifespan, and their death rate and their birth rate are going to be normal. But in years when there's a lot less food, we're going to see that they're going to die more often, and they're not going to give birth as much. We're going to see that that's going to affect that. So here we just have we have the food per mature heron, and I'll show you how that works together. But basically, how much food there is per heron divided by the normal food per heron, or how much food they would like to have, and that affecting the heron birth rate. So when there is no food per male heron as opposed to how much they would like, the birth rate would be 0, and so on and so forth. Moving up to when there is a 1-to-1 ratio, they have the amount of food that they like or need to survive, that their birth rate will be normal. Also, to point out, they never are able to exceed their birth rate or death rate, or so basically, if they had an infinite amount of food, they would not live forever. There is a cutoff for their lifespan because otherwise the model wouldn't make very much sense. So this is the construct of that right there. We have the adolescent trout and in the model, and they are basically how much food does an adolescent trout provide for a heron, and then we have the mature trout and how much food that provides, and then that's compounded into heron food, and then divided by the number of herons, and then there's your effect of food on heron birth rate, and then that's just put over on the death rate as well. Added the same kind of predator-prey dynamic for the newts. As you can see, because they're at the very bottom of our food chain, they're eaten by pretty much everyone. The newt eggs are eaten by the trout, the adolescent newts are eaten by the adolescent herons, and the mature newts eaten by the mature herons. And then, of course, because newts are now a food source for the herons, we added those into the compounded food, which will affect the birth and death rate, as well as add the same effect of birth and death rate for the trout, which now have a food source. So now newts are in there. After playing with the model a little bit, I found that some of the numbers didn't work out very much. We were seeing that populations were growing, specifically in the newts, a bit too high, and that didn't make sense for an ecosystem that has some limiting factors, and unfortunately I don't have things like vegetation or insects, which would normally limit the number of newts or the bottom consumers, so I simply added a quick fix for the time being, which were just carrying capacities for the environment. Basically, if their population got too high, it would boost the death rate and it would kill a lot of them off to represent that, not being able to hold too much. So these are the graphs that, after all of these three species were compounded together, that we produced, and as you can see, it's a pretty stable model. It starts at year 12 because there's a little bit of fluctuation at the beginning, but basically it reaches a nice equilibrium, and that's what we want to see in our model right now. Now, the step after that, of course, is to introduce our bullfrogs and see what is the impact of this invasive species. So the first thing that I needed to do, of course, was create an independent bullfrog model. This is basically what I did for everything else. It's now a 4-step aging chain, and it has birth and death rates for every one of the, or rather mature rates for the in-between steps. I also provided a separate flow for introduction. Basically, I could put in about 20, actually any number you wanted. I think I ended up settling on 20 bullfrogs, turn it on and then turn it off to represent the introduction, so it would be a constant stream of bullfrogs. And then I also, so now that I had my independent model, I made the same predator-prey dynamic, putting in adolescent trout eating the bullfrog eggs as well as the tadpoles. And then this is just the end of the model again, didn't have enough space on that slide. And this is the mature and adolescent herons eating the adolescent bullfrogs. And as I said before, the mature bullfrogs don't have any predators in the Pacific Northwest, which is why they're a really big problem here, because they're actually so big that the great blue herons can't handle them. Some of them can get up to like 2 pounds or something like that. For a frog is gigantic. We have some at my outdoor school site, and they're hard to hold on to. I, as a human being, have a hard time catching them because they're quite strong. So that's one of the biggest problems, because they're reproducing and nothing is killing them except their natural death. I also added bullfrogs into the food source for the heron. This is just that food source again. They're there as a food source for the herons, the adolescent bullfrogs rather, and then the eggs and tadpoles for the trout to affect their birth and death rates. Now, because the bullfrogs have been picked on for a while and everyone's been feeding on them, we have to add them into the equation, because they are actually a predator. They feed on trout eggs, the adolescent bullfrogs do, as well as the newts in almost every step of their growth. We have them feeding on the newt eggs, we have them feeding on the adolescent newts, and we have them feeding on the mature newts. And as you can probably expect, they're going to affect the newt population the biggest, because they're basically an entire new source of death to completely eliminate the newt aging chain. So I then, because they now have a food source, they also need an effect of food source on birth and death rate, added one of those onto mature bullfrogs as well as adolescent bullfrogs, so now the level of food affects their birth and death rate. So now that everything was together, I ran the model, and these were the graphs that I produced, and as you can see, they are quite different than the other ones. And the next slide is basically just what did I do to analyze the data. I'm actually going to leave it on the graphs right now because that's where the majority of the data is. As you can see on the first graph, up in the top left, we have the bullfrog population, both mature and adolescent. For the first 20 years, they were completely dormant, and then we see a gigantic spike, and then we see that spike die off. What's happening there is that the bullfrogs basically find the limit of the environment that they've been introduced to, and as you can see in the graph directly below that, and the graph in the top right, the new population in red drops dramatically, and that's basically what the bullfrogs are finding as their limit, is they've almost completely extincted the new population. In the graph to the top right, we see that the mature newts go from being around 3,000, 4,000, and they drop down, looks to about 0. Actually, if you see the actual numbers, it's about 300. But going from a population of 3,000 to 300 is a gigantic step down for the newt population. We also see that the adolescent newts go from being around 9,000, again dropping down to only a couple hundred, as well as the newt eggs dropping down from 200,000 to almost nothing. And what we see from that is a giant feedback system in that we're basically working our way up the food chain in terms of the bullfrog's effect. So the bullfrog have pretty much cleared out all of the newts. Now the newts are the main food source for a lot of the other creatures. So what we see here, if you look at the blue on the top right and the lower left, that's the mature and adolescent herons. As you can see, they go from being about 10 and dropping down to around 6, which for an ecosystem is quite a drastic drop. Also, the adolescent herons almost drop down to 0, simply because their food source has been completely taken away. Now, the interesting thing, continuing with the feedback loop of what's happening here, we see the effect on the trout is there's a bit of chaos there as a new predator is introduced, and then we see the herons begin to die off. We actually see that they stabilize. They're the pink there in the bottom left and the upper right. They actually stabilize a bit higher than they did before, and I was a bit shocked by this outcome. I wasn't expecting this to happen, but as I looked at it, it made a lot of sense. The only way that the trout are connected to this model is through the herons and through the eggs of the newt. They eat the eggs of the newt and they're preyed on by the herons. Now when the bullfrogs come in, they get another egg food source, so they're not really affected by the food source. But their main predator actually does end up dying off, and so because of that, their population is going to stabilize much higher. So that was the analysis of the data, and this was, it's really hard to see, it's a bit clear on my poster if you come out around 3 o'clock, but this was the whole model in its entirety, and some of the conclusions that we could make about this were that invasive species will absolutely have a widespread effect on their environment. They don't affect just one species, they end up affecting that species, which affects another species, and so on and so forth. So one of the reasons why dynamic modeling is so important because it can help track that effect and track the effect all the way. They can almost extinct a species, which can have devastating effects to an ecosystem. I don't know if any of you guys watch CSI, but one of my favorite quotes from Gil Grissom is that if all the bees in the world were to die, then the human race would follow in 4 years, basically because they pollinate almost all of our food, our vegetables, and stuff like that. So one species, while it may look like only a minor part of an ecosystem, can actually play a gigantic role in the ecosystem as a whole. There are also always unforeseen consequences. I would not have expected in a million years that the trout population would actually increase with the introduction of a new predator, especially on the same level of them. The bullfrog is considered a secondary consumer, which would be expected to be competition for the trout, but they actually end up higher up. And modeling is able to make all of these things more clear. As you can see, the model was very complex, but the data that it gives is very definitive, very precise, and gives you a lot of good insight into what's going on. I'd like to take a sec to do some special thanks to Gabriel Stuff. He helped me with this model. Diana Fisher for introducing me to Systems Dynamic, and Barry Richmond and the scholarship set up in his name. That's the reason why I was able to come down here today. Without that, I'd still be up in Portland.